Here is our paper on protection design for multi-terminal DC networks. What we are analyzing in this paper is different ways of protecting DC systems from DC faults. So we identify different means of clearing a DC fault current from a DC system. So we start our analysis with simple point-to-point schemes, so the ones that exist today, to find out about the basic ways of protecting DC systems. So this is the most conventional way to design a DC link. And by the way, for this paper we are talking only about voltage source converters, because even though we start with point-to-point schemes, in our end goal is our multi-terminal networks, which are only feasible with voltage source converters. So for a basic voltage source converter based point-to-point scheme, the principal way of protecting that system from DC fault would be by AC breakers. So if a DC fault happens, then your first response is to trip the AC breakers, which will at some point stop the fault current from being fed from the AC side into the DC network, and then eventually it de-energizes the scheme. However, it is quite a lengthy process to get that system de-energized. So you can imagine that if you apply the same sort of thinking to a multi-terminal network, you would need to trip every AC breaker around that system, and then it will be quite a long process in that system to isolate the faulty section and to come back with the healthy parts of the system running. A different way to clear a fault on a point-to-point scheme would be to have a DC breaker. So now it's a device that operates on the DC side of the converters, and one of the advantages over the AC breaker is that it operates very fast. So if you compare how long the fault current lasts between the two cases, you can see that if the DC breaker operates, it very quickly chops the current down to zero. And one of the advantages it gives you, that is, in fact, your converter is still connected to the AC system, so it can carry on operating as a STATCOM, for instance. If you apply this idea to a multi-terminal network, it's still a very good way of doing the protection, because then if you imagine having a DC breaker at every line of that system, then you have a very selective protection scheme, because then you are isolating. If, let's say, fault happens on this line, you are isolating only this line, and the rest of the system carry on running as it did before the fault. The only problem with this approach is that DC breakers tend to be quite bulky and quite expensive. A third way to clear a DC fault would be to have a fault blocking converters, what is quite often referred to as full bridge type converters. And this type of converters, they can stop fault current in a similar way as a DC breaker would. So actually they operate very fast. But again, trying to translate this idea into a multi-terminal system, the problem is that, again, you have to shut down the entire network before you can isolate the faulty section of that network and come back with the healthy parts operating. Then what we are proposing is sort of a hybrid solution where you place DC breakers only in strategic locations around the DC network. Like for this system, that would be this line between subsystem 1 and subsystem 2, this tie line. So this way you can reduce the number of your DC breakers from, say, in this system 24 to only 2. And then the way you operate the protection scheme is that as soon as you detect there is a fault on that network, you flip the tie between the subsystems. So this way, if the fault happens on the network 1, network 2 is spared from the fault, so it's isolated from the fault, and it carries on operating as it did. And then you rely on the local protection scheme for that, only for that sub-network. So effectively, the response of the protection is very fast, quite economic in the design, and then also you don't end up losing big chunks of your network for the fault duration. You only lose a small section of the network if you do it correctly. So basically, this is what we propose in that paper.